acid on trying to figure that out. So one good thing, as soon as we see acid, what does that mean?
There's a hydrogen.
We have a hydrogen. Okay. The next part, people are like, okay, fine, you got hydrogen, but is it HSO3 or is it HSO4? Right? Which is a good question, though technically both are wrong. Sorry. We have to correlate our meaning of ick.
Is it SO2?
No. What does the ick mean? When we're looking at our acids, we go to the ick ending if our complex ion, so our ternary acid, okay, ended in 8. So the mnemonic device that the tutoring center came up with is I ate too much and I got sick. There's our ick 8. I can help you kind of remember that. Which means the suffix we're looking at would be sulfate. And the formula for sulfate would be SO4. And yet I just said you were wrong. Okay. What I said was wrong was HSO4. HSO4 is wrong. What is the charge on SO4?
H2SO4.
SO4 is a -2. Hydrogen is a +1.
You're very passionate about that.
We need
Well, he
to
was making it sound like I was wrong about the SO4 part. That's freaking me out.
we need 2 hydrogens to balance. It needs to be H2SO4. Okay. Officially, to be 100% correct, because it is acid, we also need to include the phase. Our phase is aqueous. Moving on, reacted with or neutralized with, so there's our plus sign, potassium hydroxide, our symbol for potassium. K hydroxide, OH, charge on OH, -1, charge on potassium, +1. Is our charge balanced? Yes. Crap, I forgot to write aqueous up there with, here we go, real quickly. Aqueous, potassium hydroxide. So now we can write aqueous. Right. To produce, now we have to predict the products. In our neutralization reaction, we have the general form where we form water and some other salt. Okay? It's the same thing as a double replacement, so if you just focus on the double replacement, we would exchange our positively charged species for each other, and we would end up with K, potassium, next to our sulfate, plus, I gotta erase all this stuff, our hydrogen next to OH. Okay. We need to now check our formulas. The charge on potassium, +1. Charge on sulfate, -2. Is it balanced? No, we need 2 potassiums to make that formula correct. Okay. If we move to our HOH, yes, we could write that as H2O. The reason I like writing it as HOH is that I can better see the double replacement swap. Okay, we're taking the hydrogen from our acid and we're putting it with the hydroxide of the other species. Make sense? Charge on hydroxide. We said it like 6 times now. -1. That might have been an exaggeration. Hydrogen. Is our formula balanced? Yes. Can we do some predictions on phases? Good. Answer was yes. Yeah. What kind of phases can we predict on both of those?
HOH be aqueous.
HOH, I heard aqueous. What does aqueous mean?
Water. And water.
Aqueous means dissolved in water. So we have H2O, also known as water dissolved in water.
Sounds more like liquid to me.
It's better to reference that as a liquid instead of as aqueous. Okay. What about K2SO4?
Aqueous.
How do you know that was aqueous?
Because potassium is one of those ones that mixed it.
This goes back to our double replacement reactions, the solubility rules. Potassium is a group 1 metal. All group 1 metals in compounds will always be water soluble, which means aqueous. Okay? So you have to use those solubility rules to predict. You've now drawn your equation. You'd still be wrong in answering the overall question because the overall question was we want a balanced equation. Is the equation balanced? No. So how do we balance? It's not officially how we balance, but I'll kind of accept that. And
The 2 in front of each.
right. Do we need to go through the steps on balancing? Everybody's got it. Okay. That is all of our reactions. Okay. We're now going to open up a big can of worms, almost, because it sounds like you got a question.
For the 2 HOH, the 2 applies to everything after that. Up
The
until
2
A.
applies the H and the OH.
Okay.
So about the big can of worms?
So, if we go backwards to our single replacement reactions. Remember how we talked about in, what was it? Whenever we talked about single replacement reactions, and we mentioned in lab made this question a little bit more difficult because in lab, you looked at reactions like this. Right? Where you didn't have a compound, but you had ions forming in your reaction, right? Sound vaguely familiar? Okay. So when we look at this reaction, we went to try and predict and balance it, we would notice that it balanced out outright and we didn't have any problems with it. Okay. Let's do a very subtle change to this. I'm going to introduce silver ion into this. So instead of forming lead, I'll end up forming silver metal. Would we expect this reaction to work? Silver is what? Very active or very inactive? Very inactive, which means the metal, or silver, being non-reactive, wants to be by itself. Okay, not in a compound. Well, nothing specified in a compound, so that doesn't help us. Our other rule was saying not charged. Where is silver not charged? On the product side. Does this reaction occur? Yes. Okay. We're trying to shift or move to the reaction where silver is neutral all by itself. This reaction does occur as written. Okay. For the lecture's sake, I will give you compounds because I think that makes it easier to evaluate, but it is going to address the next issue. Is this equation balanced? Okay. How do you know it's not balanced? Good. Dang, have you guys been reading ahead?
We've been reading at the proper pace.
Oh, good job. If we went through and looked at this, and our old method, silver versus silver, 1 and 1, right? Our atoms balance. So it looks balanced. But it's not balanced because charge does not equal out. We should also be including a charge line when we look at our equation. On the left-hand side, what is our charge? A +1. And on our right-hand side? +2. Does the charge balance? No. We need to come up with some way to balance the charge. Okay. Why is the charge unbalanced? How are we getting charge? How do you define charge?
Number of electrons.
It's our balance of electrons versus our protons. We change the number of electrons, we're changing our charge. So what's happening in the course of this reaction is zinc is going to become zinc +2. To become zinc +2, what does zinc have to do?
Loses 2 electrons.
It has to give up 2 electrons. It's the only way it becomes positively charged. Right, but what does it give up those electrons to? Something must accept those electrons. Why? Electrons are point charges. They have no mass, incredibly tiny, and they're charged. That means they are incredibly unstable. We will never see an electron floating on its own. It must be counteracted by something. So if zinc gives up those 2 electrons, something must accept those 2 electrons. What is that something in this case? The silver has to accept those 2 electrons. But if we look at silver, we're going from silver +1 to silver 0. What happened in that case? It only gained 1 electron. So what happened to that extra electron? In our equation, we don't know what happened to it. We haven't balanced our equation properly. So one option was just to say, okay, well, I need to add an extra electron then. And I could add an extra electron here because it wasn't used. But what did we just say about electrons? They can't be by themselves. I cannot include an electron in the equation. So what ends up happening? I will need 2 silvers to react. Okay? And I know that was incredibly obvious. And you're like, oh yeah, duh, that was obvious, right? Are you really going to accept the one guy saying yeah? Really? Because I can just skip ahead. I don't have any problem with that. Okay? It's not incredibly obvious to most people, okay? And I don't expect you to see that. But what we do have to acknowledge is that it doesn't balance. We have to come up with a new way to approach and balance questions. And this is going to require looking at the balance of electrons versus protons on any individual element. Okay? In a single replacement reaction, it is a special type of reaction known as redox, or reduction and oxidation. So we now have to come up with some understanding of what is redox. And that is where we would move into chapter 17. Oh, that's right, I told you to read that, didn't I? Okay. So there's our oxidation and reduction chapter. So any reaction that involves the transfer of electrons from one atom to another, or one unit to another unit, is a reduction or oxidation reaction. So in this case, we've got another reaction here. This one's known as a it's actually still a single replacement, believe it or not. It looks a little bit weird. Okay? And it looks weird because hydrogen is our metal that's causing the single replacement. So we would expect hydrogen all by itself, but hydrogen all by itself is a diatomic element, so it has to be written as H2. Okay, so it complicates matters. Okay, but what's happening here is we're doing a redox reaction or a single replacement reaction. We need to come up with some way to recognize and acknowledge how that is happening. Okay, so we're going to introduce a new concept here. We're going to look at the oxidation state, okay, also known as number. So you'll hear me alternate back and forth between those. I can't be consistent, sorry. Okay. And that is different from charge. Okay. Unfortunately, they are very closely related, but they are entirely different concepts. The oxidation state or number applies to an atom. Okay. So if I look at a molecule and I want to know the oxidation state for hydrogen in H2, I need to look at the atom of hydrogen and say, what is its oxidation state? If I want to know the charge, what is the charge? Well, the charge applies to the unit. Where do I have the charge written? What's that? Superscript. The upper right-hand corner. The charge is always, always, always given to you. What is the charge for H2? What's written in the upper right-hand corner? Nothing is written in the upper right-hand corner, which means the charge is 0. There's nothing there. If it was positively charged, what would I need to write up there? A +1, okay, or just a plus. Okay. The issue again is that sometimes your charge and your oxidation state or number equal the same thing. Okay, so we need to come up with ways that we can go through and look at this. Okay, so first off, we need some rules to go through and apply these. What's that?
More rules.
Yeah, more rules. There are a lot of rules that your textbook lists out. Most cases we can dodge a lot of these rules. So they list rule 1, any atom in its elemental state has a 0 oxidation state. Okay? Which is actually kind of a dumb rule because rule 4, rule 4 will tell you the answer to 1. Okay? Rule 2, any monatomic ion, the oxidation number equals the charge on the ion. Okay? Also solved for in rule 4. Okay? So that's not a very useful rule. The next part comes into what's happening with our nonmetals. Our nonmetals will very typically carry negative charges. Why will they carry negative charges? What are all our nonmetals trying to look like? The noble gases. How do they look like noble gases? Gaining electrons. So they are very typically negatively charged. Okay? So as a general rule, you should be seeing them negative. There are some things that stand out that you have to watch out for. The biggest one, oxygen will carry a -2 oxidation state. There's one exception to that, which we won't see in this class, so don't worry about it. Oxygen will always carry a -2. Okay? Hydrogen will very typically be a +1. Okay? Again, probably for the sake of this class, you can memorize hydrogen's a +1. Halides, So our halides were where on the periodic table? Pointing at the periodic table was sort of useful. It's the column underneath fluorine, chlorine, bromine, iodine. Those are our halogens. Okay. If we make them halides, they've gained an electron, so that's why we changed the name. It's no longer the neutral halogen. It has an extra electron, so we have a halide. Okay. Again, very typically that. The one big exception, when they're bound to oxygen. Okay. Why? Oxygen is more electronegative than most of the halogens, meaning oxygen is going to take the electrons instead of the halogen. Right? And then the last one, the sum of the oxidation numbers equals the charge on the molecule. Everybody kind of freaks out at this. You've already done this. We've actually used this equation already. Anybody remember where we've used this before? Nomenclature, balancing our formulas. We used a very similar formula. And in that formula, I said it was the sum of the charges on each of your pieces equals the overall charge. Okay. Why did I not say oxidation number outright? Because the rest of this stuff is confusing as all hell and it freaks you out. Okay. So we stuck with charges because we could kind of work our way up to it. It's the same formula system that we used for nomenclature. Okay. So, things that we can do. Know your ionic charges from ionic compounds. Okay, this goes all the way back to nomenclature. Okay, so sulfate has a -2 charge. You need to know those ionic charges. If you don't have those memorized, this will make defining your oxidation numbers very, very difficult. Okay, oxygen will have a -2 charge. And then pretty much the last thing you can look at, sum of the oxidation numbers will equal the overall charge on that unit. All right? So let's pick a couple quick examples here with the equation we've got in front of us. I want to know the oxidation number for calcium in that first unit. Okay. Is it an ionic compound? No. Okay, so rule 1 doesn't work. Rule 2, is there oxygen? No, so rule 2 doesn't work. Rule 3, sum of the oxidation numbers equals the charge on the unit. Okay, so I'm going to take a look at my formula there, and I say, okay, well, I want the oxidation number for calcium, so I'm going to solve for it. So I don't know what it is, I'll use a variable. The variable I will use will be, way to just volunteer something. Let's make it X. Okay. How many calciums are in that unit?
1.
So X times 1. Okay. What is the next element in that unit? Okay, as a hint, the unit was boxed in. What is the next element shown on the screen?
Calcium.
We already counted calcium. What's the next element? There isn't one. That's it. It's just calcium. Okay? This has to now equal what? The overall charge. Where's the overall charge specified? Nope. Overall charge. Charge is always, always, always given to you in the upper right-hand corner.
So 0.
It is 0. What is the oxidation number for calcium?
0.
0. What was rule 1 from the previous slide? Any atom in its elemental state has an oxidation number of 0. What is calcium solid? An element in its elemental state, which means? 0. The formula solved for it. You don't need an extra rule. The formula gives it to you. Okay? Because you are always given the charge. Try a little more difficult one? Sure, way to jump in there. Let's not go that difficult. I lied. We're going to go that difficult.
Go hard or go home.
Yeah, might as well. I want to know the oxidation number. Actually, this one's not that bad. Oxidation number for calcium. Two ways to go through and solve. We can go through and solve the long way. Sum of the oxidation number for all of our elements added up equals our overall charge. So, how many calciums are there? 1. Do I know its oxidation number?
Well, not here.
I don't know it yet. It's x times 1 plus, what's the next element? Oxygen. Okay, do I know the oxidation number of oxygen?
Negative
How many oxygens are there?
2.
Plus hydrogen. Oxidation number for hydrogen was
Plus 1.
plus 1. That's not except for when it was with oxygen. Okay. Plus 1, how many hydrogens are there?
2.
What does this have to equal? The overall charge in this case is 0. Can you solve for x? I'm hoping you said yes to that.
I did.
Thank you.
None of my breath.
I appreciate that. X equals,
6.
try again, plus 2. Okay. Go ahead. The negative 2, you mean this negative 2?
Oxygen.
That's oxidation. Oxidation number of oxygen is always a negative 2.
Rule number 2.
Rule number 2 gets us the negative 2. The positive 1 is the oxidation number for hydrogen, which actually isn't in our rule set here, but on the previous slide I told you what it was. Okay, and we'll come back to that. The 2 here means there's 2 hydrogens. Okay, so what we've done is the oxidation number of our element, calcium, times the number of them. How many calciums? 1. Oxidation number for the next element, oxygen, times the number of them, 2, plus the oxidation number of the next element, hydrogen, times the number of them.
So
That equals 0.
Not just the hydroxide?
Calcium, there's only 1.
Oh, okay. I understand.
You're on the right page? Okay. So we end up with the oxidation number for calcium being a plus 2. Okay. What did rule number 1 say? Know the charges for the ionic compounds. So really what that's saying is that instead of looking at calcium hydroxide, we could look at this as what? Calcium plus 2 and hydroxide minus 1. There's my unit. I don't know its oxidation number times how many of them are there in that unit,
1.
times the charge, or equals now the overall charge.
Plus 2.
What is the oxidation number for calcium?
Plus 2.
Get the exact same answer either way.
Why couldn't,
Go ahead.
why couldn't you just look at the table?
So looking at the table is where you can run into misleading things. The biggest issue comes down to your nonmetals. Right? The metals you were required to be able to figure out charges on, and it turns out that charge in most cases is equal to oxidation number. Okay? Most cases. What happens if we look at nonmetals? Are you required to know the charges in covalent compounds? None. In covalent compounds, you are not required to know the charges. That's why when you write out the name for sulfur dioxide, what's the di mean? 2 oxygens. There's no charge information. We haven't specified charge. And that's because we can't just memorize the charge from the periodic table. Our metals, as long as they're put with nonmetals, their charge will equal the oxidation number. So it's relatively straightforward to figure those out. Where it becomes problematic is when we're looking at the oxidation numbers for nonmetals.
Are we going to say
Yes. Okay.
non-metals?
So here we go. Charge, oxidation states, or numbers. Okay. So let's take a look at charge. You should be able to tell me the charge for every single one of those formulas relatively quickly. Starting with the first one, we have charge. 0. Next one. Plus 2. Next one. Negative 1. Next one. Negative 2. The charge is always given to you straight away right in that upper right-hand corner. Nice and easy. Okay. What about the oxidation state? Okay. This now applies to each element. The oxidation state should be something that you always calculate. Okay? And in some cases, the calculation is trivial. And you're like, well, why did I have to bother doing that? Couldn't I just write out the number? Okay? As long as you get it right, sure. Let's run with that. So what is the oxidation state for the first one? 0. How do you know it's 0? According to what I just said, you have to solve for it. All right, so we start with x, I don't know what it is, times how many? How many of coppers are in that first unit? There's only one of them. That then equals the overall charge. What is the overall charge? 0. The oxidation number then is 0. How about the oxidation number for the next one? Ends up being plus 2. X, 1, plus 2. X has to equal plus 2. And now the trick question, what is the oxidation number for the next one? What's that? I have to change the question. Oxidation number applies to the element, not to the formula. So I now have to define the oxidation number for each element in that formula, and there's more than one element. Okay? The standard that most students will go to is try and use charge. What is the charge on nitrogen? Typically. -3. What is the charge on oxygen?
-2.
How many oxygens are there?
3.
So the charge contribution from oxygen would be what? -6. What's the charge contribution from nitrogen? -3. We add that up, what charge would we get? -9. Is that the charge on nitrate? No. Why not? Because the oxidation number is different from charge. So let's work that one together. So we will go through and approach this the same way we've been doing everything else. Okay. Let's write out our general form first, the number of our element, or the oxidation number for our element. How many, or what's the oxidation number for nitrogen? X, I don't know, times the number of them. How many nitrogens are there? Okay. Plus, bear with me here, the oxidation number for oxygen. Y, thank you. We will come back to -2 in just a second. Okay. Times the number of oxygens equals -1. Upper right-hand corner, the charge is given to us. Can we solve this equation outright? No. 2 variables, 1 equation, impossible to go through and solve. Okay. So we need some more information. What was that more information, Sam?
Oh, it's
The
oxidation -2.
oxidation number for oxygen is a -2. So really what we're saying, Y equals -2. I now have 2 equations, 2 unknowns. I can substitute in. I get X plus -2 times 3 equals -1. When I go through and solve, I get X equal to, I don't know, there's some fancy calculations got to do in there, algebra, plus 5. Okay. Yes?
What was the -2 for oxygen?
That's our rule. Oxygen will always have a -2
Oh, okay.
charge. Or sorry, oxidation state.
Gotta remember oxidation state.
Sorry? We'll come back to that statement in just a second.
What is oxidation?
So the oxidation state is the balance of electrons and protons in an element. Okay. What is the balance, or what is charge? The balance of electrons and protons in a molecule. Okay. That's when we go through to do Lewis structures, we put our electrons on the most electronegative elements first, because it's how do the electrons disperse themselves through the molecule. That's charge. Okay. Oxidation state or number is how are the electrons dispersed on an individual element. And depending on what that element is connected to, it may end up giving up electrons or taking electrons.
What does that plus 5 mean?
So that plus 5 means, which is what Haley
Yes.
was asking,
Yes.
what did X equal?
Oxidation state, right?
X was our oxidation state for nitrogen. So what does plus 5 mean? That means when we look at nitrogen in nitrate, what happened to it? It gave up 5 electrons to what? to the oxygens. Okay? Why would it give up those electrons to oxygen? Oxygen happens to be more electronegative than nitrogen, meaning the oxygen is going to rip the electrons away from the nitrogen. That means the nitrogen will have to have lost those electrons. Okay? So our oxidation number gives us some information about the balance of the electrons that it has associated with it in an individual compound based on how it's arranged with other elements. Okay?
Do you have to have oxygen in there to do this?
To get an oxidation number for nitrogen, in this case, you would need oxygen. Do you always have to have oxygen to determine it? No. Your oxidation number can be defined with any combination of different elements. Okay? And it's ultimately all going to come back to applying these same sets of rules. Okay? Questions about that? Can you guys do the sulfate on your own?
Yeah.
Okay. So everybody's got it? We'll start with sulfur. Do we know the oxidation state for sulfur? No, so it's an X. How many sulfurs are there? 1. Plus the oxidation number for oxygen. Okay, -2. I'm fine to go ahead and skip with that as long as you guys are. You okay with that?
Yeah.
Okay, how many oxygens are there? 4. What does this then have to equal? -2, because in the upper right-hand corner it says -2. We then go through to solve. We get X minus, well, I don't know why I was about to write 4. Equals -2. Solve for X, and X becomes +6. What did we say X meant? Don't say +6. It's the oxidation state for our sulfur. Yes. So sulfur in this case had to give away 6 electrons to make sulfate. What's a negative number? What is the oxidation state for oxygen? -2. So our oxygen did what? Took 2 electrons from our sulfur. Okay? So it's just looking at that balance of our positives and negatives. Questions about that?
So if you asked what the oxidation state of the oxygen is, we'd just say -2. Like we wouldn't say because there's 4 oxygens.
So the charge contribution from oxygen would be a -8. I'm not asking for the charge contribution, I'm asking for the oxidation state. The oxidation state for oxygen is -2. Okay. Throw something kind of crazy at you real quickly here.
If he was a baseball player, I bet his favorite positive one for the curveball.
Oh my God, panic, freak out. What is the oxidation number for that oxygen? -2. Oh, okay. Well, that was too easy. How about that oxygen?
-2.
That one. That one. Do we care? Oxygen is always a -2. Don't get bogged down on a loss of all this other junk that's happening. Why is it there? To throw you off and make you panic. Think back to your standard rules. Use the rules. I don't care what the rest of the structure is. Oxygen carries a -2 charge. Make it -2. Make sense? Did you guys find something? No? Okay. Just check it. So, what can we then do with this? Oh, shoot. So, all close your eyes real quickly. La, 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 la. You want to look at anything? So,
Was that the can of worms?
this is our part of our can of worms, yes.
Just as we haven't even all of it.
So now what we want to do is look at a reaction and decide what happened to the reaction. Okay? Does it fit an oxidation or reduction reaction? Well, what's happening in oxidation reduction is we're transferring electrons from one element to another. So our oxidation numbers must change. Well, how do we know the oxidation numbers change? We know they change because we determine the oxidation numbers. So here we go. 3 elements, Determine the oxidation number for each of those elements in the reactant. Determine the oxidation number for each of those elements in the product. Okay? This time I'll give you a hot minute. Wherever there's confusion, we can come back to it. So what is the oxidation number for oxygen in the reactant? -2. Oxygen in the product. -2. And we know that because that's the oxidation number of oxygen. Always. Just stick with it. Okay? Now we have to go through and deal with our solves. Which do you want to look at first? Or actually, was there anybody getting a different number for iodine in the reactant? You got a different number or the same number? What did you get for iodine? +5. Which was? Perfect. You got the exact same, or I see what you were saying maybe. +5. You got the right answer. Good job. Let's stick with that. Okay. How about in the product? 0. So as soon as we hit questions, you got to be like, I don't agree with you, right? We're going to do that?
Yeah, I'll tell you.
Okay.
Sure. Wait, Mike.
I'm not really nervous about you. What's that?
So in the product, the first one's not going to have a charge, right? Is that what it's-
The iodine in the product will not have a charge, or an oxidation number. It'll be 0. Okay? Its charge is also 0, which is why it ends up with an oxidation number of 0. Okay. And carbon in our reactant came out to be a +2. Carbon in our product came out to be +4.
Yeah, that was almost hard. Almost.
Okay, so since we had an almost hard, let's go ahead and check that one. Let's take a look at the CO2. We'll start with the carbon. How many carbons are there? Oxidation number, sure. How many carbons are there?
5.
Carbons, interesting point. Okay, you brought in 5. What does the 5 apply to?
Both the carbon and the oxygen.
Both the carbon and the oxygen. Okay, so we can go through and multiply that by 5, but we're going to end up multiplying both numbers by 5. So what could we do to simplify that?
Parentheses and 5.
Don't multiply by 5.
Alright.
Just ignore it altogether. You'll notice that when I boxed in that final one, what did I not box in? The 5, because it applies to both, I don't have to include the 5. If you include it, it'll still work. You'll still get the same answer. Your calculation is just going to become a little bit more difficult. Okay? So how many carbons are there? There's only 1, plus -2, because it's the oxidation number for our oxygen. There are 2 oxygens, so as we jump ahead, this then equals our overall charge, which is 0. When we go through to solve, we get x minus 4 equals 0. X equals +4. If you go through and include the 5, it's not going to change your calculation. It's just going to make your or change your answer. It's going to make the calculation a little bit less obvious, if you will. Okay. X equals 4 is relatively straightforward. You probably had to get x equals 20 over 5. Plus 20 over 5, yeah. Which, theoretically, you can do that calculation, but it's more difficult than just saying 4. Make sense? Okay. So what we've now done is determine the oxidation states for all of our elements. We now want to address what happened to that element. So take a look at iodine in the reactant. Started at a +5, meaning it had given up a lot of its electrons to oxygen. In the course of the reaction, what happens to it? It becomes iodine 0. How does it go from a +5 to a 0?
Becomes another.
A reaction happened. What is that reaction? Specifically, what is changing? It had to gain electrons. We'll ignore the number of electrons for the moment, but it'll gain electrons. That's it. That's all we're saying. What happened to the oxygen?
No reaction.
Nothing happened to it. So we won't even worry about it. No change. What happened to the carbon? It lost electrons. It went from a +2 to a +4. To become more positive, you had to lose electrons. That is an easy mistake. You look at the number getting bigger, you go, oh, it must have gained. Remember, you're gaining and losing a negative charge. So you have to watch out for that minus sign. Okay? So we could then go through and look at our reaction saying, well, we have a gain of electrons in one case, a loss of electrons in the other case. That takes too many words. Chemists are lazy, so we come up with another way to look at this. Okay? What happened to iodine's oxidation number.
There, it's from 5 and then.
To go to a +5 to a 0, what happened to it? It dropped. It decreased. It was
+5.
reduced. Guess what we refer to what's happening on the iodine? It was a reduction. Its oxidation number was reduced. Went from a large number to a small number. Okay? What happened to the carbon?
Oxidized.
It increased. So we could call that
Oxidation.
biggered. Okay. That doesn't quite work. So we ended up coming up with a different term. The term we end up using is oxidation. Okay? Don't use bigger. That's not a good idea.
Would you mark
Okay.
it off in biology?
Probably not. We have oxidation. Why do we call it oxidation?
Loss of electrons, oxidation.
Yeah, why does loss of electrons sound like oxidation? Doesn't make any sense, right? Stop saying biggered.
Started it.
That's my new favorite word now.
English teachers must hate me. Oxidation. Ox sounds a lot like oxygen. Let's take a look at our carbon. In our reactant, how many oxygens is it bound to? 1. Take a look at our product. Carbon, how many oxygens is it bound to? 2. What did we do? We increased the number of bonds to oxygen. Okay? We oxidized it. Okay? The names reduction and oxidation, ultimately oxidation was the first one discovered because oxidation, we noticed, corroded metal. Okay? When our metals started to react with oxygen, we just had them out in the atmosphere, they started to decay and fall apart. But when we removed the atmosphere, they stopped reacting. So we said it was oxidation. Okay? A reaction with oxygen. Not all oxidation reactions involve oxygen. Oxygen just happens to be kind of the biggest contributor to our oxygen reactions. It was the first one we observed. Once we had a better understanding of reversal of those processes, and in particular, electrons, we could then start to come up with the opposite term for reduction, and there we used a little bit more sense in naming it because we could look at our numbers changing. Okay? Oxidation was something discovered ages ago. When did we discover electrons? Recently, 1900s. Okay? That was Thomson's experiment, right, with the cathode ray tube, seeing electrons. 1890, 1900. That's a significant gap in time. We don't have any comprehension of our oxidation numbers until the last probably 100 years, 120 years. Okay? So, we now need to add to this a memorization because we need to be able to know that when we reference oxidation, we are referencing a loss of electrons for our species. When we look at a species and it gains electrons, we need to be able to call it out and say a reduction happened. So you need to be able to tie those two terms to each other. This again comes back to mnemonic devices. I personally think the coolest one is the one that's already up there. Leo says grr, because Leo is a lion, which is a big cat, and cats growl. There you go. Leo says grr. There we go.
I got a better one for you, oil rig.
It is so not better. That one is awful. But apparently, most of this campus uses oil rig, so I will at least include that. Okay. You know, I'm a little too green for oil rig. Okay. Oxidation is loss. Loss of what? Exactly, it doesn't say. Leo, loss of electrons is oxidation. Oh, it's electrons I'm losing. Okay. Leo says grr. Heck of a lot better than oil rig. You lose. Okay. Either way, as long as you tie those concepts to each other, I'm fine with it. You need to have those concepts nailed down. Okay. Kind of make sense? Okay. Because here's the next big can of worms, right?
Stop with the can of worms.
Sorry. Oxidizing agent. Okay. What is an oxidizing agent? An oxidizing agent caused something else to be oxidized. If something else was oxidized, what happened to the original species? It was reduced. So an oxidizing agent is actually reduced in the reaction.
Oh, that's annoying.
Yeah, I agree.
Oh.
Okay. A reducing agent caused something else to be reduced, which then means it itself was oxidized. Okay. So to go through and process these types of questions, you have to determine your oxidation numbers. Once you've got the oxidation numbers, you can then decide, was it oxidized or reduced? Once you've decided that and you're being asked about agents, change the term around and you now have your agent. Okay? Questions about that? Good, do some practice. So within this, identify the oxidation states all the way through. Yeah, give me the oxidation states. Tell me if it was oxidized or reduced. And then I identify the oxidizing agent and the reducing agent. Oxidation number for tin plus 4.
Plus 4.
Oxidation number for iron plus 2.
Plus 2.
Plus 2. What we now want to do is take a look at the connections between those. So tin plus 2 goes to
10 plus 4 is
tin plus 4. So what happened to it?
It lost electrons.
It lost electrons.
It's a Leo.
Loss of electrons, thank you. Is a Leo, we have oxidation. If we take a look at the iron went from plus 3 to plus 2. What happened to it?
It gained an electron.
It gained electrons. So it GERD. We get the GERD back. So we've got our reduction.
It biggered.
Bigger.
Now the hard part, dealing with our oxidizing agents. So we can reference tin plus 2 saying that it was oxidized in the course of this reaction. But what did it cause iron plus 3 to do?
Gain.
It caused iron plus 3 to gain electrons.
So it was reducing agent. Is that what you're trying to get?
So tin plus 2 is the reducing agent. Because it caused something else to be reduced. The iron plus 3 is the oxidizing agent because it caused something else to be oxidized. It does not make sense. Don't even pretend. Okay. If you see ing agent or ant is the same thing as ing. You're looking at these opposite deals. That you're causing something else to do whatever the term says. Okay.
You're going it that way. Because I had it the other way. Soul electrons from another compound molecule. That's why it was
Next thing we want to be extra specific on with the agents. The agents will refer specifically to the compound that contains the element. So for this first case, the agent is the same thing as we would imply, and it's just tin plus 2. Okay. But what happens if we move to a more complex formula? Say like the nitrate. Okay. The nitrogen was reduced in this next case, so it was the oxidizing agent. Okay. But I won't say the nitrogen was the oxidizing agent because was nitrogen there on its own? No. When we're referring to the agents, we're referring to the species that forced the reaction to occur. So in the next case, our agent, in fact our oxidizing agent, is the nitrate ion, the entire complex of the nitrate. Okay? Not just nitrogen. The agent will always refer to the molecule. It will also typically refer to the reactants, not the products. Okay? So it can help you kind of subclassify and keep that a little bit simpler. You have the rest of the answers up here on these. I would highly encourage you to test these when you get home. We still have time, so we're going to go through and whip through something kind of nasty, and you can ask questions about it on Thursday. Okay? So if you don't get any of those correct or you have questions about those, Thursday you need to be checking. We'll start off class looking back over these, making sure you've got them nailed down. Questions about that? Good. Agents will always mess you up. There's anything you can do about it. Freaking spies. Balancing redox reactions. Okay? Sometimes it's trivial. So when we take a look at this equation, can we balance that equation easily? Yeah, we look at it. There's one zinc, hydrogen. I just need a 2 there, and now it's balanced.
What is it?
Okay. Is it really? So the one thing that we added to this was checking the charge. What is the charge on the left-hand side of the equation?
No.
Zinc brings in a 0 charge. Hydrogen brings in a +1, but how many hydrogens are there?
2.
Charge on the reactant side? Positive 2. What is the charge on the product side? Positive 2. Do the charges balance? Yeah. So sometimes it's trivial. You can just look at it and you can help work your way through it. Other times, like in this case, it's not quite as trivial. Because we look at the tin, we look at the iron, we have the same number of elements on both sides, but does the charge balance?
No.
We get 5 on the reactant side and +6 on the other side. Okay? This makes it much more difficult to balance. So when you encounter these types of redox reactions, what we can do is split these. Okay? And that's not the most fun. Reduction will never occur on its own, because in a reduction you have to gain electrons. Where'd you get the electrons from? Another element. So that other element had to do what? Give up the electrons, which means it was oxidized. So when we typically refer to our reduction and oxidation reactions, you almost always hear it referred to as redox, okay? Or reduction and oxidation. We never just say reduction or oxidation, because both of them have to happen at the same time. That can make it more difficult to balance. So what we'll do is, for the sake of balancing, we will split the equation. And what I'm going to do is split it into the pieces. One piece where it is just reduction, and in the other piece where it is just oxidation. Once I've got them split, I will then go through and balance those individual equations using electrons, which is challenging because we said we can't create or destroy electrons. But those electrons will act as markers to balance the overall equation when we add the two equations together. Okay? So we'll shift to our half reaction. So I'm going to group, let's see, what did I do? I did iron first. I'm going to take iron, and I'm going to look at it going to iron +2. And I could look at tin +2 going to tin +4. If I added these two equations together, what would I get? The equation I have up top. If I add iron +3 to tin +2, I've got the exact equation that's written. So all we're doing is going to try and set this up. We're separating them out so that we can see them cleaner. To balance each equation, I now need to add electrons to the appropriate side of the equation to make sure my charge balances. So let's look just at the iron +3 to iron +2. Okay? That charge doesn't balance, so I'm going to adjust the charge by adding in electrons. How are electrons going to adjust the charge? What's the charge on an electron?
Negative.
Negative. Will that change the charge?
Yeah.
Yeah, because it's charged. Okay? So where do I add the electron? Okay, well, guess. I'm going to add the electron to the right-hand side. What is the overall charge now on the reactant side? +3. Nothing changed. What's on the product side?
+1.
+1. Did I get closer to balancing the charge or further?
Further.
Further. What does that mean?
No, that's it.
I put the electron on the wrong side. Charge on the left-hand side? +2. Right-hand side? +2. My charge is now balanced. Yes, I've introduced this electron, this mystical electron that has just appeared out of nowhere. Okay? Where did it appear from? The tin. So I now will go through and look at the tin. Now I want to look just at the tin. What happened to the tin? That says +2. That should be +4. Okay. I need to add 2 electrons to the product side. Why 2? Balance out the charge appropriately. Okay. I could then add these two equations together. When I add these two equations together, what happens? This electron, our electron on our reactant, will cancel with one of the electrons in our product, and our overall equation becomes, come on now, this. What is the issue with that? I can't have an electron chilling by itself. That means I need to go back to my equations and I need to adjust the equations so that when I add the two equations together, what happens to the electrons? They cancel each other out. They're balanced. So to do that, I will multiply that top reaction by 2. So I'm going to run that top reaction twice. By running that top reaction twice, how many electrons are consumed? 2. How many iron plus 3s are consumed? How many iron plus 2s are produced? 2. That's going to change my coefficients to the whole equation. Now when I add them up, what happens to the electrons? The electrons on being opposite sides of the equation cancel. Everything else stacks up, and I end up with this new equation. Let's check to verify that I balanced it properly. We do that by doing what? Charge. And technically the elements. So what's the charge on the reactant side? Plus 2, plus 6, right? So we get plus 8. On the product side, what do we have? Plus 4, plus 4, plus 8. Is my charge balanced? Yes. Are my elements balanced? Yes. I've now balanced the official equation. This can make it easier to balance redox reactions. Okay? The textbook does not give you good examples at this. What I would recommend, let's see, you use the 2 examples that I've given you for balancing practice. So, Thursday, we're going to look at this balancing practice, and we're going to look at that redox sheet, which was way back here. Oh my gosh. Whoops. And this one. Those are the 2 things. Make sure you're prepared for that. I don't know, I might throw out a quiz.